Good morning. Today I'd like to talk about some fixed point analysis, which is going to have a direct bearing on some of our numerical methods. If you think about it, our numerical methods consist of taking an initial estimate for the solution to the problem that we're interested in, doing some procedure, getting a new and improved estimate, at least we hope that it's new and improved, and then repeating the process in an iterative fashion. So we're going to start off by saying what we mean by a fixed point. A function g has a fixed point at x if g of x and x are the same thing. Another way of thinking about this is procedure-wise. You have a fixed point if, when feeding a number into function g, you get that same number back again. For example, the function g of x equals 2/3 multiplied by x plus 1 over x. I want to investigate whether or not that has any fixed points. To start with, I'll observe that x equals 0 is not a fixed point of g because g isn't even defined at x equals 0, but x is. So I don't have to worry about x equals 0 at this moment. I want to decide, is there an x so that g of x is the same thing as x? This is just an algebra question. So we write down what x equals g of x would actually mean. That means that x would be 2/3 times x plus 1 over x. This is an algebraic equation. Multiply by 3, divide by 2, and you'll find out that 3/2 x is the same as x plus 1 over x. Subtract x from both sides, and you'll find out that 1/2 x is the same thing as 1 over x. That says that 1/2 x squared is 1, which says x squared is 2. So this original function g does have fixed points. It has 2 of them. One of them is at radical 2, and the other one is at x equals negative radical 2. If you put any other number into g of x, you won't get that same number as your output. So given a function g that has some fixed points, select some number x1 and define x2, x3, x4, and so on in terms of function values for g at the previous x. So x number 2 is going to be g evaluated at x1, x3 is going to be g evaluated at x2, x4 is going to be g evaluated at x3, and so on and so forth. Since everybody has had calculus 2, you'll recognize that we're generating a sequence here, and sequences may converge or they may diverge. The relevance of this is that if we furthermore assume that g is continuous, at least on the collection of x values that we're interested in, and if the sequence of numbers x1, x2, and so on converges to x, the thing that it converges to must obey x equal g of x. So in this fixed point iteration, as we're going to call it, in this x number k plus 1 equals g of x number k, suppose that g is continuous, at least on the places we're interested in, and that the sequence of numbers actually converges to some limit x. If you take the limit of both sides, because g is continuous, the limit of g evaluated at various x's is g evaluated at the limit of the x's. That's part of the definition of continuity. If the limit of the x's is x, this next to last line just says x equals g of x. So if our fixed point iteration actually converges to something, the thing that it converges to is a fixed point of the g function. For example, here's a g function. G of x is 2/3 multiplied by x plus the reciprocal of x. Does it have any fixed points? Set x equal to g of x, do the algebra in case we forgot. X squared is 2. X is either negative radical 2 or radical 2. It's the positive one that we'll be looking for. A couple of comments are in order. If you have a certain xk and you have a positive xk and you feed it through this result, xk plus 1 is going to be positive as well. And secondly, I don't need to worry about getting close to 0, because if x were to get close to 0, xk that is, were to get close to 0, then x number k plus 1, which includes a term that's the reciprocal of xk, will be far from 0. So if I start off with a positive x1, I don't have to worry about this thing approaching 0, where the g is undefined. If I do fixed point iteration based on the function that we were just speaking of, if I take x1 to be 1.5, then x2 is g of x1, which is 2/3 times 1.5 plus 1 over 1.5. I did the arithmetic on my calculator, and the result is 1.4 repeating. X number 3 is g evaluated at x number 2, which is 2/3 times the 1.4 repeating number plus 1 over that number. After doing the arithmetic, I found it to be 1.424501.425. X number 4 is what I get when I take this number, x number 3, and feed it through the g function, which works out to be 1.417667,616, and so on and so forth. By the time I get to x6, I have 1.414. Those digits are correct. Those match the digits in square root of 2, and these digits are not correct. So this suggests to me that this idea is working. If I want to find a fixed point for this function, I selected some particular estimate x1 and begin feeding it recursively through the g function, and the numbers that I get appear to be settling down to square root of 2, but as you can see, it's doing it in a very slow manner. It looks like you would have to do a lot of these to get much accuracy. Not all fixed point functions are created equal. I'm going to have another one. This g of x is going to be g of x equals 1/2 x plus 1 over x. Like before, this is simple enough that I can find out what the fixed points are. If you set x equal to g of x, you'll get x equals 1/2 x plus 1 over x. If you rearrange that, that says that 1/2 x is 1 over x. Multiply both sides by x, multiply both sides by 2, and you find out that x squared equals 2. So I have the same two fixed points that I had in the other g function. Just as before, I'm going to take x1 to be 1.5, then x2 is equal to g of x1, which is 1/2 times 1.5 plus 1 over 1.5. which using my calculator worked out to be 1.41 and then an unending string of sixes. If you'll notice, this already agrees with square root of 2 to 3 significant figures. The 1.41 is correct. Take x number 2 and feed it through the g function, multiply it by 1/2 and add its reciprocal, and you end up with 1.414215686. Calculate x number 4, you get g of x3, which is 1.414213562. On my calculator, I saved x4 into the x register and then used it to calculate x5. Visually, x5 and x4 are identical to each other, but if I subtract one of them from the other as stored in my calculator, I find out they differ by about 1.6 times 10 to the negative 12 power. This second choice of the g function is a lot better than the first one. The convergence appears to be very rapid, while on the other hand, the convergence on the first one was very slow. At the moment, we have no way of understanding why that is, or even how we could have predicted it ahead of time. So now we want to do some analysis. I have to ask you to remember some stuff from the first semester calculus course. In case you don't remember, I'm going to remind you of what the mean value theorem is. This is something that you learn in Calculus 1. You do some really pointless problems involving it, and then you forget about it. We're going to need to understand this mean value theorem, though. So here we go. The mean value theorem says this. Suppose that you have a function g of x, and it has a continuous derivative on the interval from a to b. Then there's an x value somewhere between x equal a and x equal b that has the property that g prime at c is the difference of the values g of b and g of a divided by the difference b minus a. This is the mean value theorem. What in the world? So imagine that you've got the graph of function g. On one end, I've got x equal a and y equal g of a. On the other end, I've got x equal b, that is, and y equals g of b. The slope of the dotted line that connects this end to that end is g of b minus g of a over b minus a. And all the mean value theorem really means is, if your function g is really nice looking, has a continuous derivative, then somewhere in there, there's a place, which I'm going to label x equals c, where the slope of the tangent line, f prime of c, is the same as the slope of this other line, the dotted line. The mean value theorem just says somewhere in here, the tangent line is parallel to the dotted line. That's all that that language actually amounts to anything in terms of meaning. So what does this have to do with anything? In particular, what does this have to do with what we were talking about, which was fixed points of functions and fixed point iterations? Let's suppose that capital R is a fixed point of some function g. That is to say, R equals g of R. Also, I'm going to assume that g has a continuous derivative, if not for all x values, at least for x values that are close to R. So there's some little interval of x values upon which I can do derivatives, and those derivative values don't act too badly. I want to think about how different an estimate in my fixed point iteration is as compared to the estimate previous to it from the actual value that I'm trying to find, how different these estimates are from R. So if you write the fixed point iteration, xk plus 1 equals xk, if you subtract R from both sides, you find out that x number k plus 1 minus R is g of xk minus R, which by itself is not very helpful. But remember, R is a fixed point of G. R and G of R are the same number. So this tells me that x number k plus 1 is G at x number k minus G evaluated at the fixed point. So far, this is nothing that I can relate to anything else that I can easily think about, but it's almost there. Here's the trick. This right-hand side, G of xk minus G of R, that should remind you of something if we remember what the mean value theorem looks like. That almost looks like something in the mean value theorem. It's the top of the fraction that we referred to in the mean value theorem. So we think to ourselves when we see this, it's too bad that G of xk minus G of R is not divided by xk minus R. So our sneaky trick is divide it by xk minus R and also multiply it by xk minus R, and you get the same results as before. Of course, in a code, you would check to see if xk was actually a fixed point of the g function before you did this, in which case you would stop, and if it isn't, you would go on with your calculation. Xk plus 1 minus R is the slope of that secant line that we were talking about times xk minus R. By the mean value theorem, this fraction is equal to g prime evaluated at c for some x number c between x number k and where you're hoping to end up at. People usually take the absolute value of these quantities so they don't have to worry about positive or negative signs. So the absolute value of x number k plus 1 minus R, which is a measure of how different x number k plus 1 is from the answer that we want, this is exactly equal to how different estimate number k was times this number, absolute value, g prime at c. The convergence or divergence of the fixed point iteration is going to be controlled by how g prime acts. For example, suppose that you always knew, no matter what x you stuck into the derivative, that the value of the derivative was never much different from 0.5, then this would say the distance between iterate number k plus 1 and the answer that you're after is about 1/2 times the distance from the previous estimate to where you want to end up, and you would get behavior just like bisection. But it doesn't just have to be 1/2. If you knew that g prime of x never got bigger than 0.7 and never got smaller than negative 0.7, then the error at step number k plus 1 couldn't be any bigger than 7/10 of the error at the previous step, and you'll get roughly bisection-like behavior again, except it's not going to be quite as good as bisection. Bisection guarantees you that the error at the next step is no more than 1/2 times the error at the previous step. But in any case, if I know that the derivative is small, then things are good. On the other hand, if I worked out a formula for g prime of x, and I was able to determine that it's always, say, at least 1.4, that says the error at the next step is actually bigger than the error at the previous step, and things are not going to go well for me. In practice, things are usually not that nice, though. In practice, the best that you can hope for is this sort of situation. If g prime at r is less than 1 in absolute value, and if g is continuous in the interval from a to b, the continuity says the size of absolute value g prime x can't suddenly jump from being less than 1 to bigger than 1. There's no discontinuity in it. So within interval from a to b, there must be a smaller interval, which also contains the r, so that when you look at the derivative, the g prime is less than 1 in absolute value because of the continuity. If you pick your initial x1 in that interval, alpha to beta, then the fixed point iteration is going to converge on you. This is very important to us. This is how we're going to see how certain algorithms converge or don't converge. Much later, when we talk about iterative methods for linear systems of equations, we'll have something very much like this, except we'll have some matrix norm instead of the absolute value of g prime. So for fixed point iteration, if g prime is bigger than 1, I'm going to get divergence. If g prime is less than 1 in absolute value, I'll get convergence. I don't want g prime in absolute value to be real close to 1, though, because then my convergence will be slow. So if g prime were close to -1 or +1, that would be bad. Convergence is bad in this case. Outside -1 to +1, I'm going to get divergence. I don't want to be outside. I don't want to be inside and close to 1 or -1. I want to be close to the middle. If I can convince myself that g prime has a very small absolute value close to the middle, I'll be happy. Also, the smaller, the better. One of the fixed point methods that we talked about earlier was based on the fixed point function g of x equals 2/3 times x plus 1 over x. If you remember, we saw that that method seemed to be converging if I started at x1 equals 1.5, but it was going rather slowly. Let's figure out why. The derivative g prime at x is 2/3 times 1 minus 1 over x squared. Even if I start with x1 close to square root of 2, the behavior is going to be determined by how big g prime at square root of 2 is. If you work through the algebra, you find out that g prime at square root of 2 is 1/3. This means the error at step number k plus 1 is going to be 1/3 of the error at the previous step. So the thing will converge, but it will converge slowly. On the other hand, we had that second fixed point function. The fixed point iteration for it, starting at x equal 1.5, converged very rapidly. Let's investigate that one. If you take the derivative of 1/2 x plus 1 over x, you get 1/2 minus 1 over x squared. And if we evaluate that at x equals radical 2, which is our fixed point, we find out that G prime at radical 2 is 0. And remember the situation we said? We want the G prime to be between -1 and +1. We want to stay away from the -1 and +1. We want to be as close to 0 as we can manage. And it turns out for this particular iteration, that is what happens. G prime at the fixed point is 0. So we are, in terms of G prime, where we want to be. This is why this thing converges so rapidly. I got to make a caveat though. G prime is 0 at the fixed point, but maybe not at other places. Since this is getting a little bit long, I'm going to stop here. Next time, we're going to do a generic analysis of Newton's method, not just to find square root of 2 though. That's been our example. We're going to look at the nice case first, the not so nice case. We'll look at a modification of Newton's method that can at least partially fix the not nice case. And we'll look at some Fortran. We'll look at some refinements to the false position code. So if you haven't put that in your computer yet, be sure to do so. We'll talk again another time.